Welcome to the session on regression, correlation and hypothesis testing, exponential models. The objectives for this session are to understand different kinds of exponential models in bivariate data and estimate coefficients in an exponential model using a change of variable. Recall the exponential relationship a to the power x equals n can be written in terms of a logarithm, log n base a equals x. Logarithms can be used to explore and manage non-linear trends. Let's take a look at an example. We begin by plotting this data. X against y equals 3 to the power x. This is clearly non-linear data. Let's see what happens when we take logs of the y values. So here's x and y equals 3 to the power x, and now log y. Now let's plot this. Clearly, if we plot log y against x, we get some linear data. So here's the non-linear data, and here's the linear data towards the bottom of the screen. The data goes from non-linear to linear data by just taking logs. So if we have an equation of the form y equals a times b to the power x, how do we convert it from non-linear to linear data? Begin with a non-linear relationship, y equals a times b to the power x. Then take logs, and remember that log base 10 is simply written as log. So log y equals log a times b to the power x. Then use the multiplication law. We have log y equals log a plus log b to the power x. Next, use the power law. So in this equation, we simply convert log b to the power x to x log b. And now compare to the linear form, y equals mx plus c. The capital Y equals log y. This is the dependent variable. The capital M, or the gradient, is log b. Remember, b was just a constant, so therefore capital M is a constant. X is the independent variable, so capital X is also the independent variable. And log A is equal to the intercept, or capital C. So here are the dependent variables, log y, or capital Y. Here's the constant, or gradient, log b, or capital M. Here are the independent variables, x or capital X. And here's the constant term, log A or capital C. Now let's take a look at an example. Y equals 5 times 3 to the power x. Clearly this is in the form ab to the power x. If we convert this from nonlinear data to linear data using the formula on the previous slide, we get that y equals 5 times 3 to the power x becomes log y equals log 3 times x plus log 5. So if we sketch these graphs, here's the equation y equals 5 times 3 to the x plotted on a graph. And here's the equation log y equals log 3 times x plus log 5 plotted on a graph. Clearly this is linear. The gradient for this graph is log 3 equals log b, and the y-intercept is at log 5 equals log a. Now let's take a look at another non-linear relationship, y equals ax to the power n. How do we convert this to a linear relationship? So let's begin with y equals ax to the power n, and then take logs. So this gives us log y equals log ax to the power n. Next, apply the multiplication law to give log y equals log a plus log x to the power n. And then use the power law. So we have log y equals log a plus n log x. And now let's compare to the linear form. So capital Y, the dependent variable, equals log y. Capital M, the gradient, equals little n. Capital X, the independent variable, equals log x. And capital C equals the constant term, is log a. So here are the dependent variables, capital Y and log y. The gradients, capital M and little n. The independent variables, capital X and log x. And the constant terms, capital C and log a. Let's now take a look at an example. Y equals 2x to the power 1.5. This is clearly in the form ax to the power n. We will convert this from non-linear data to linear data using the formula on the previous screen. So y equals 2x to the power 1.5 becomes log y equals 1.5 times log x plus log 2. Here's a sketch of y equals 2x to the power 1.5. Clearly, this is nonlinear data. If we now use the form log y equals 1.5 times log x plus log 2, we get linear data. We've plotted log y against log x. In this equation, the gradient is n, which is equal to 1.5. And the y-intercept is at log 2, which equals log a. Let's now give a summary of both these cases. Recall that the case 1, we had that y equals ab to the power x can be converted to linear data by using the formula log y equals log bx plus log a. And the second case, y equals ax to the power n, can be converted to linear data by using the equation log y equals n log x plus log a. Let's now take a look at an example. The table shows data collected on temperature T in degrees C of a colony of bacteria with its growth rate g. Using changes of variable x equals t and y equals log g to code the data, the regression line of y on x is found to be y equals 0.09 plus 0.05x. Pause the video and have a go at the questions shown on your screen. When you are ready to view the solutions, press play. Let's take a look at part A first. Suppose that the data can be modelled by an equation of the form g equals ab to the power t, where a and b are constants. Find the values of a and b and interpret the constant b in this equation. So let's solve this. we know that y equals 0.09 plus 0.05x can be written as log g equals 0.09 plus 0.05t. We've simply replaced y by log g and x by t. And so, if we raise both sides to the power 10, we have 10 to the power log g equals 10 to the power 0.09 plus 0.05t. This can be rewritten as 10 to the power 0.09 times 10 to the power 0.05t. And therefore, since 10 to the power log g equals g, we have that g equals 1.23, which is 10 to the power 0.09, times 1.12 to the power t, which is 10 to the power 0.05t. Therefore, we have that a equals 1.23 and b equals 1.12. In this equation, b is the rate of change of g per degree. Now let's take a look at part B. We are required to comment on the reliability of the estimate for growth when the temperature is T equals 40 degrees C. Notice that in the range of temperatures we have in the data, the maximum is T equals 28 degrees C. Therefore, since 40 degrees C is outside the range of the data, the model is not a reliable estimator for growth at this temperature. This is an example of extrapolation. This brings us to the end of this session. If you have understood its contents, you should be able to understand different kinds of exponential models in bivariate data and estimate coefficients in an exponential model using a change of variable. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.